So remember that what we're trying to do is we're trying to show that these two sets are equal. And we did the first part of the proof in the last two videos. So now let's look at the second part of our proof. So what do we need to prove? That number 2, we need to prove that A minus C union B minus C is contained in A union B minus C. So again, we're going to start with our outline. We're going to figure out the proof and then we'll write it out formally after that. So what would the start of this proof look like? Well, I'm going to take X to be in A minus C union B minus C. And then I need to end up showing that X is in this other set here. So let me leave some space. The end of my proof needs to be that X is in A union B minus C. So let's work a little bit backwards here at the end. What does it mean to be an element of A union B minus C? You need to show that X is in A union B and X is not in C. So let's go back to the beginning and we got to fill in from the start to the end of this proof. So let's look here. If I'm in this union here, I know that either X is in A minus C or X is in B minus C. So here we're going to split up into cases, and the cases are going to be based off of this first set here. So case 1 would be that X is in A minus C. And then the opposite of that will be case 2. So the opposite will be X is not in A minus C. So let's start with case 1. If X is in A minus C, that means X is in A, and X is not in C, right? But if X is in A, then I know that X is in A union B. So what do I have? I have that X is in A union B and X is not in C, and that's exactly what I needed to get to. So we finished case 1, so now let's look at case 2. Well, case 2, I knew that X was in A minus C or X was in B minus C, but right here we said X is not in A minus C. So if it's not in the first one, it has to be in the second one. It's in B minus C, which tells me that X is in B and X is not in C. But if X is in B, then I know that X is in A union B. So what do I have here? X is in A union B and X is not in C. And again, that is what I needed to get to over here to get to my end. So I've outlined the proof, and now let's write the proof formally. So we're going to write out the proof here. So use your outline as a guide. Let X be in U such that, look at the start of your outline. My start of my outline right here. X is in A minus C union B minus C. And then what was my next line in my outline? It said, then X is in A minus C, or X was in B minus C. And from here we broke off into cases, so we will consider two cases. And what were those two cases? X was in A minus C, or X was not in A minus C. So here's where you're going to split off into your two cases. Case 1, we suppose X was in A minus C. All right, look back at our outline. That means X is in A and it's not in C. But since X was in A, we said X was in the union, A union B. And since X is in A union B and X is not in C, X is in this difference, A union B minus C. And that was the end of case 1. So now look at your outline for case 2. For case 2, we said the start was suppose X is not in A minus C. Since we knew that X was in A minus C, or X is in B minus C, the fact that it's not in A minus C means that it had to have been in B minus C. Then what does it mean to be in B minus C? We said that meant that X was in B. It's not in C. Again, throughout this whole thing, I'm referencing the outline. I just can't flip to it in the video. But look back at your outline. In case 2, the next thing we said is that since X is in B, X is in A union B. And now what do we have? We have that X is in A union B and it's not in C, and that's exactly what it means to be in the difference of A union B minus C. So that completed case 2. And if you look at both of the cases, we had the same conclusion. So you'll say in either case, X was in A union B minus C. And what have we done? We've proved, hence, A minus C union B minus C is contained in A union B minus C. So we've completed that proof. But if you put this part together with the previous part, what we've actually shown is that these two sets are equal. So we've actually shown that these two sets are equal. If you put the first proof and the second proof together, that will be what we have proven.